Hello, everyone. You want to learn about how to build a conversational AI solution with NVIDIA NeMo? Watch this video. My name is Alireza Darbehani. I'm a machine learning engineer and the stream owner of the ML engineering and ML ops at ACE. We are fortunate to have Christopher from NVIDIA and two great facilitators today. I'll just go through an introduction of our speaker and great facilitators. Our speaker, Christopher, has a PhD in computational linguistics from University of Toronto, and he's a senior deep learning applied scientist at NVIDIA. Gordon, as our first discussion facilitator, he's the lead machine learning engineer at Ada, which offers a market-leading chat automation platform to help non-technical teams offer powerful support experiences at a scale. Zach is also a data scientist and NLP stream owner at Aggregate Intellect. He's passionate about applying machine learning and NLP in building AI products. Without further ado, Christopher, please take us away.
Thanks very much. All right, let's get this shared. Okay. Well, thanks for the very kind introduction, and thanks for bringing me here. So I am Chris Parisien. I'm an applied scientist at NVIDIA. Waiting for this to actually show properly. There we go. So I'm an applied scientist at NVIDIA. I'm in a group doing conversational AI. My background is in NLP. I actually spend most of my time these days working in healthcare, but we handle a lot of different verticals. So let's get into this. So what do we mean by conversational AI? So there's three main components in this when people normally talk about this. So typically we're going to start from speech. So audio, we're getting audio, turning that into words. We might take those words, that text, and do some work with that. So on the NLP side, we can talk about language understanding, named entity recognition, question answering, a lot of different tasks we can do on this. Once we then have an answer from that, we want to take that text and put it back into speech again. Now, conversational doesn't always just mean chatbots. That's a lot of what we do, but really applications built on this can have any subset of these components. We do a lot of work with partners who are working in contact centers, doing transcription of contact center calls. We do batch work with customers who are looking at like biomedical text and these enormous batches. There's a lot of different things that we can do from this. So NeMo is one framework that we have that works very tightly with two other components, and these all work very, very closely together for people who are trying to build these conversational models. So for most people who want to build these kind of models, let's say they've got some of their own speech data, and they just the off-the-shelf speech recognition isn't quite good enough for them, and they want to do some fine-tuning on their own data. And then they want to deploy that. The best place to start for them is with a package that we have called the Transfer Learning Toolkit. So TLT is like a zero coding setup, relatively simple to use. You just say, okay, here's my data that I've got. I've processed it. I want to start from this kind of checkpoint. I want to do some fine tuning on that, and then we want to deploy, and off we go. If you want to do something a little bit more detailed than that, we're going to get into NeMo. So this is what we're going to be talking about today. NeMo is actually what's going to end up running in TLT under the hood. So these two are going to be working very, very closely together. NeMo is much more of an applied research toolkit. So it sits on top of PyTorch, works with PyTorch Lightning, and this is a real modular kind of setup for doing work in these models. We give you a lot of really good checkpoints to start from, model architectures to start from, for doing a lot of different work in speech recognition, NLP tools, text-to-speech tools, and it also lets you do iteration on these models for things like, I want to play with different loss functions, I want to set up my data sets differently, I want to set up different metrics. This is the framework you want to work in for that. This is for people working at more of an intermediate to advanced level, researchers, people who might know some PyTorch, don't necessarily want to spend all the time in the great details, but really want to be able to iterate on their experiments very quickly. This framework is fully open source, and we'll get into exactly what that means for this application. And it's an important part of how we operate. When you actually get your final models and you want to deploy them, we've got an app for that. Jarvis is our solution for serving up these conversational models. Now, what that specifically is going to be doing is it takes your model that you've trained, it effectively compiles it. So it does a lot of the automated optimization, quantization, memory management. It'll also handle things like load balancing, fault detection in the servers that are deployed. So these three all work together, and we have handled deployments of this at extremely large scale in terms of the size of the model, how much we've trained on it, but also scale in terms of like how big these server environments are that are serving these queries in real time. So NeMo is available now. It's on GitHub, fully open source, and we developed this fully in the open. And that's something really important to keep in mind with this. There is no private fork of NeMo. If you actually go to the GitHub site for NeMo and you kind of look at people's individual branches, you can see everything that we're working on. There's nothing hidden here. We've been getting some pretty good uptake of this in the community. NeMo is relatively young. We're at 1.0 beta now. We'll be reaching full 1.0 release later in the spring. We've been getting some pretty good adoption already across a lot of different open source libraries. We work very closely with PyTorch, with the Lightning team, with Hugging Face. We work closely with a lot of different data labeling tools as well. We've gotten some good uptake from independent software vendors, from startups, and also some really big enterprise deployments. So the problem, if you're working on conversational AI models, is the state of the art changes really fast. You can easily drive yourself crazy by trying to follow what's happening on archive. Every week or so, there's a new model that comes out, either an ASR, language understanding, and speech synthesis. If you're doing research in this, you need to be able to iterate on those very, very quickly. The problem too is that there's a lot that's going on in conversational AI, but the toolkits that are out there either don't really have very good support for these kind of models, or they do, but the level of abstraction is very low, so that when you want to try to hook things together, you get these like non-compatibility issues, you get redundant code. So we're trying to really simplify these things. So what we give you is we give a framework that's built on top of PyTorch. So we pick up all the normal Cuda acceleration that happens in PyTorch. We're built on top of Lightning, so that really simplifies a lot of the code structure, handles the training loop for you. We use Facebook Hydra to simplify the configuration of these. And then on top of that, we give you libraries. It acts like a model zoo and like a component zoo. So when you can pick existing model architectures, you can swap out components of them. You can pull pre-trained models. So we have our cloud container environment called NGC. There's lots of pre-trained models you can pull from that. This really is intended to make your life easier, gives you enough flexibility to do your experiment, but also just accelerate that process. So we call them neural modules. So that's what NeMo is. It's neural modules. These are the building blocks for building these models, for building these architectures. Now, every module, as we call them, it is a subclass of a Torch module. So a lot of what you know, if you're familiar with Torch modules, it will carry over. But we layer on a few new functionalities on top of that. We have a strict typing system. Now, so we'll talk about what that means, but that simplifies the connection of one module to another. So we give you typed inputs and outputs to catch a lot of errors that you might otherwise miss. We add serialization that's handled from those Hydra configs. So when you want to serialize, you get not just the weights, but you can also serialize all the other like ancillary components that might go along with the model. And we handle a lot of other file I/O that handles that as well. So that really simplifies things. So I'll walk us through a few more of these features and how this works. Really, the type system is one of the core tenets of the way this operates. When you hook these components together, the neural types will catch errors and give you far more informative answers, far more informative responses about what's going on. So this helps you catch a lot of errors like, okay, I've got, say I've got an encoder that's going to output a tensor. It's a three-dimensional tensor, but I'm going to hook that up to a decoder, and I don't know whether those are all the same dimensions. So here, we label each of those dimensions with types, and that will catch those errors. It also handles things like, so it'll catch like the semantics of each of those dimensions in the tensor. It'll catch like concatenation errors that you've got, dimensionality mismatches. So say you've got like, a module that's spitting out like, it's expecting an image of like 224 by 224, but the thing that you're hooking it up to is 256 by 256. Well, it'll catch that for you. So you don't have to then spend a week trying to figure out what's going on. The configuration, models are all configured through Hydra. That makes this experimentation far simpler. So you can do those that configuration programmatically, but you can also just handle this through YAML files. So any of the architectures that we give you in this package, there's a default YAML file that goes with that. We flag a few key parameters that you will need to change, like, oh, where's my data? But then it's also very simple to go, okay, I'm expecting my input to be in 16 kilohertz. I'm expecting, here are the vocabulary labels that I'm going to be using, and here's the tokenization that I'm expecting, right? This is what is handled very nicely through this. People who have done this kind of work in PyTorch and in Lightning before likely have gotten used to the notion of doing mixed precision training. This is a big lifesaver. So for those who haven't done mixed precision training before, when you normally, by default, you go and set up your model and you want to learn some weights, those are going to be all represented in pretty large floating point precision. So typically like 32-bit floating point. Now, it is slower to do multiplication in 32-bit floating point. So one of the nice things that you can do is you can reduce the precision of that in certain cases. Some of the operations, you can bring it down to 16-bit. You can bring it down to, integer, 16-bit integer, 8-bit, sometimes even 4-bit integer. And PyTorch can do that automatically for you. And it works very, very well down into the CUDA level. So this automated mixed precision, you can just say, I want to use automated mixed precision at this level of optimization, this level, and it will just compile that for you. So this gives you really, really big speedups. We also automate scaling out to multiple GPUs and also multi-node. So when you're doing big models and very large data, this is another lifesaver. So this simplifies things quite a lot. So very, very high distribution of this. And some of the models that we have, we'll talk about some of these a little bit later. Some of them the models themselves don't even fit in one single GPU. So we will also end up handling the model parallelism in this as well. So one of the most common kinds of use cases that people run into when they're using our framework is fine-tuning for ASR. So like I said, we get a lot of partners, customers, people who want to do speech recognition, and they're doing this in a particular domain. So let's say you're running a contact center for some insurance company. So you're getting calls coming in, people are asking about, like health-related issues, and there's going to be particular terminology in there. So you're going to get differences in terms of like, there's going to be a lot of like speakerphone and cell phone kind of conversation. So some of the quality is going to be there. The noise in the background is going to be different. Vocabulary, like I said, is going to be different. So you want to do that fine tuning. Often these are customers who have quite a lot of their data of their own. And it's not that expensive to go and transcribe enough data to do some training. So the typical steps in ASR, your input is going to be a WAV file, an audio WAV file. Extract some features into that, push those into an acoustic model. From the output of the acoustic model, then do some decoding on that, calculate the probabilities of some different possible phrases. Maybe you'll use a language model to re-rank that, and you get your output. When you're fine-tuning this, it's a pretty straightforward process. You got to prepare your training data. We can give you some scripts to help you do that. So from that manifest, that training data manifest, we can then download a pre-trained model. So we have lots of good pre-trained models that we can give you, and then just run a fine-tuning script. This is really just like a couple lines of a script to get that working. And then you can export that into a format that Jarvis can take, deploy it, and off you go. So like I said, preparing your data is probably the most important thing that you're going to want to think about in this situation. There's a lot of good best practices around preparing that data, and typically one of the biggest things you want to do is you want to augment that. This is your free data, so use it. We give you a lot of scripts to handle this. So let's say you've got, I don't know, 100 hours of data sitting around. Augment that. Do speed perturbation. So have some samples that are 1.2 times the speed, some that are 0.9 times the speed. So stretch that out. Add some noise to that. Add other artifacts. We've got a tutorial for you on the GitHub page that can show you how to do this. Lots of scripts that are in there to help you out. We've also got an integration coming soon with the DALI library. This comes from NVIDIA, and this is what's really going to handle a lot of that. It really super efficient data loading, so that will simplify a lot of those processes as well. NGC is our cloud environment for distributing Docker containers of these compute tools, pre-trained models. We've got Helm charts, lots of different things to really simplify this kind of deployment. We have a very long list of pre-trained models that are available. This is just a very small snippet of them. But we have trained models using a lot of them using just free data that's out there that we've handled for you. We also have some proprietary data that we've pulled in together that we use to train these models to give to you. So it saves you some of the cost of buying some of that data as well. So we've got speech recognition models for English, for Mandarin. We have a lot of NLP models, pre-trained checkpoints for BERT. We also have fine-tuned models for certain NER tasks, certain classification tasks. We have a few different text-to-speech models that are out there. You can go pull these. Again, these are free. NGC is worth checking out. You can just sign up for it as a guest. You can take a look and see what's in there. This is all free. So why don't we take a quick pause right now? We have some more that we'll go through, but we're going to take some questions. There should be some questions that have been coming in from the team.
Yeah, I actually have received some questions. So let me just check out the notes. One of our audience asked which languages the NeMo support, probably in different components.
Yeah, so the for speech recognition, we have released pre-trained models already for, like I said, English and Mandarin. And I think the BERT models are in English. I believe they're all just in English. Now, that said, we have trained in many other languages, and through our partners, we have also, our various customers of ours have also trained in many, many other languages. We've had good results that we've seen in Russian. We've done German. We have done, I believe we've done Japanese. There are many more in the pipeline too. I'm going to stop there because I'm probably going to start to forget which ones we've released and which ones we haven't released yet. But there are a lot more coming in the pipeline.
Perfect. Based on our previous conversation, I know you guys are really interested in the open source contribution. Do you think, or what is the process of, some, like let's say a research group can contribute to, providing more languages, let's say?
Oh my goodness, you would be our favorite people. So we absolutely love it when people make contributions. So if you wanted to contribute models, probably the best thing to do if you want to do something like contribute models is to actually just reach out to us, and we'll have a conversation about the right way to do that. But yeah, certainly if we're looking forward to people being able to contribute not just code, but data where appropriate, models. There's definitely a path that we can find to do that. So please reach out to us. There's contact information available on the GitHub page. If you've got my contact information, you can reach out to me and I'll help out.
Sounds good. I would love to give the chance to our facilitators if they have any questions so far.
I have some questions that might be suited for later in the presentation.
Okay.
Anything from you, Zach?
Well, let me jump in for a little bit. So I see that the framework is mainly targeted toward applied research scientists who needs a better way to iterate multiple models, especially for chatbots. So can you sort of like summarize and help me understand how this framework is better than just using PyTorch?
So if you are the kind of person who enjoys and is very efficient at working directly in PyTorch, I commend you. And you are a far more efficient person than I am. The intent here is to remove a lot of the boilerplate and just to make it easier to iterate quickly. So our whole research, so we have quite a large research team internally that develops new architectures. So some of the examples that we're looking at here, like Jasper and QuartzNet, these are architectures that came out of our team. Our team does that research work directly in NeMo. So yes, it's the platform that we are building to release, but it's also the platform that we use to do our own research. And the reason for that is that through the use of those collections, those module collections, it simplifies a lot of that work of reusing things like data loaders and metrics and loss functions and like all of that stuff that's there. And it really just simplifies a lot of that.
Yeah, I think that's a pretty good response. I feel like when we're developing in PyTorch, there's a lot going on, and you have basically a lot of flexibility, but then it comes at a cost of not having the time to be able to experiment.
Like it's worth remembering too that when so a lot of the experimentation that we do here is saying, okay, I want to start with this basic kind of architecture, but I want to add something new. I want to do something else different with it. So what you're doing there when you do that process is often you're writing a new module. So you're going to extend one of the modules that we already have here, and then you're writing PyTorch, right? So you are still working in PyTorch. But it's just a lot of that other stuff is taken care of for you. You're still doing work in PyTorch. This is not like we just remove that level of abstraction entirely.
Yeah, so that makes a lot of sense.
Maybe a follow-up on that would be what custom ML modeling do you think at the moment might be difficult to achieve just through NeMo, and maybe would be an area people would still need to rely on PyTorch and other things?
Yeah, I mean, like what we have focused on. So it's also worth thinking about, like when we originally built NeMo, we built it to be agnostic to the underlying framework. So we built it to say like, okay, you could have PyTorch as the engine underneath, or you could have TensorFlow as the engine underneath. And we removed that because it just wasn't helpful. So by just aligning ourselves more directly, that made velocity a whole lot better. But I think a lot of the stuff that you're going to have a hard time with is the stuff like outside of this kind of the world of like doing, ASR, doing the standard NLP tasks, doing the TTS. So like we're doing a lot of work right now on machine translation. we are developing quite a lot in NeMo to be able to do machine translation. If you were to do that ahead of time, or if you do that before we developed all of this, it would be a little more upfront work. If you wanted to do things like, there's a lot of interesting work going on right now about like working with like graph neural nets. Well, that's not necessarily going to fit very well in NeMo. You could interface them because it's all still PyTorch, but you're gonna run into some more challenges. I think what this is really intended for is the people who are like, I need to do some work. I need to train some models. I'm happy with the kind of state of the art that's there in terms of how to handle these kinds of tasks. When I want to stretch outside that and do the things that are outside that realm, that's where you're going to start to run into some challenges, or not so much challenges, but that's when you're just going to have to know more PyTorch, because then you're just going to be doing more directly in PyTorch.
Got it. So maybe for some of the more custom architectures, it'll involve people doing a bit more of their own implementation, potentially in parallel with NeMo code.
Yeah, but like a lot of the, so like a few weeks ago, I did an experiment where I needed to extend BERT pre-training. So this is a method of taking an existing BERT checkpoint and you drop in like a metric loss function, and you do continued pre-training using metric loss function, and that then gives you an embedding that you can use for a whole bunch of other tasks. Okay, well then that's interesting. But NeMo was actually really well suited to that, because most of what I needed to do was I needed to create a new data loader. Okay, well that's pretty straightforward to do from how Lightning deals with data loaders, and that was nice. And then I needed to write a different loss function. So in PyTorch, wrote a loss function for that, and plugged that in, and that was pretty straightforward. But that was very much a non-standard kind of NLP task, right? So like there's still quite a lot that you can do that doesn't have to take you that far out of the realm of this.
Great. Is there any further question? I got one from our audience here. Somebody asked, if I were to deploy a backend that uses NeMo, what are the options? Basically, in particular, if I were to take advantage of NVIDIA's Tensor Cores across multiple GPUs, is there a way I could deploy it easily on, let's say, cloud providers like AWS, Azure, or Google Cloud?
Yes. I mean, we already do that, right? So like NeMo is already going to be using, Tensor Core optimizations just out of the box. And if you actually go and check out the GitHub site, the tutorial notebooks on the GitHub site, you click on those, they go and they get launched in a Google Colab environment. So that's living on cloud. It's pretty straightforward to actually go and do that kind of deployment on cloud. So we offer, if you wanted to actually pick this stuff up, you can do installation straight from cloning the GitHub, or you can pull Docker containers. So we've got nicely built Docker containers with all the dependencies and everything you need, and those are freely available on NGC. So if you want to actually go and do some training on a cloud provider, that's probably your easiest approach.
Perfect.
And to touch a little bit more on that, can you give us sort of like a better understanding about what the difference between just using a typical Cuda and using Tensor Core? Like, why is it an advantage?
So the nice thing is that gets to be transparent to us. But the real difference between by which I mean like this is handled like close to the hardware level, right? But the difference between a Cuda core and a Tensor Core is like a Cuda core is much more general purpose. It's a single stream processor for handling relatively general purpose operations. A Tensor Core is like a specialized Cuda core that will handle specifically matrix operations in a given type. So you will have, FP32 Tensor Cores, and you get FP16 Tensor Cores, and you get int8 Tensor Cores, and there's a new type in the A100 now that's called TensorFloat. So it's TF32, and I think that adds some sparsity or something like that. So Tensor Cores are just highly optimized so that it just really massively increases that throughput for doing those specific matrix operations. But then, deciding what matrix operations to be done for what different thing, that gets to be handled transparently. So we highly recommend do your training on V100s and A100s whenever you can, and it'll do better.
And can you give us like a number, like by how many degree of magnitude do you think?
I don't have those numbers in front of me. I will forget. But so for example, just like doing the automated mixed precision gets you like 4.5, 5 times speed up on average. I mean, it really depends on the kind of network you're training. But yeah, I mean, like the individual operations, like on the, like if you actually just go look up like, oh, how does Ampere architecture work, they'll give you some nice numbers on that. I recommend checking out that reference, but I will get them wrong if I tried to spout them right now.
Sounds good.
Shall we move on to, we've got a second half of the talk, and then I guess we'll take some more questions later on.
Yeah, we should. I just was not able to unmute myself here.
So
go ahead.
All right, so let's take a little lightning tour through some of the more recently added models in here. So there's quite a lot of different model architectures that are in there. Because we are doing active research in this team, we are in the habit of adding new architectures on a pretty regular basis. So the speech recognition that we have had in there for a while is intended for these fairly large models and doing very open-ended kind of ASR. There's a fully other end of that spectrum as well. When you start looking into like what can we run on low power sensors that can be like always listening, and where we only really need to worry about like fairly simple speech commands. So MatchboxNet is a massively scaled down network for handling that use case. So this is a task that's often called keyword spotting. But this is for the kind of thing where like you've got like a smart speaker that's just gonna be like, I don't know, controlling your TV or your lights in your house or something like that. So it's a relatively small set, fixed set of commands, and you're trying to take an audio signal and classify it into one of those commands. So MatchboxNet is a much scaled down model. Fits on these very low power sensors, so you can run it on like little Jetson devices, which is very cool. We have speaker recognition as well. I draw your attention to this highly detailed and complex diagram. 2 main tasks in speaker recognition: who's speaking, and are you who you say you are. So this is trained on Voxelab data sets, and that's a helpful thing that we've put in. We're going to have building on top of this in the pipeline as well. We've got speaker diarization coming as well. So that's the task of, if you've got one stream of a conversation, saying, okay, this is speaker 1, this is speaker 2, now we're back to speaker 1 again, now we're going to do speaker 3. That's what diarization is. So that'll be coming soon, built on the same architecture. We have better voice activity detection. So this is one of these core tasks that you have to do when you're doing ASR. Given your signal, you really want to figure out like what is audio that has speech that I want to actually try to recognize, and what is silence, and what is other noise, and so forth. Typically, the first pass is everyone does things just based on activity level. So we now have a better voice activity model built on MatchboxNet, that tiny speech command model that I just showed. So this then does the task of figuring out which samples in the audio to send to the model, when we should be closing the microphone and stop listening. Megatron's very big. So there's been a ton of news over the last couple of years about language models, neural language models getting larger and larger and larger. So this is our framework for training very, very large language models. I personally was entirely thrilled that we decided not to name it after Sesame Street characters, but That's just my bias. So this framework works across a lot of different kinds of architectures. So you can use this for GPT-2, you can use it for BERT, you can use a lot of those kinds of ones. So we've trained like multi-billion parameter versions of this. There are far, far larger ones the team is working on right now that I can't say any more about, but you'll see them. This has gotten very, very good state-of-the-art accuracy on a lot of different tasks. So the nice thing in NeMo, so we've got some pre-trained models for Megatron BERT, and NeMo will also handle that model parallelism for you. So not just dividing across GPUs to handle different sets of the data, but also dividing the model itself. We also trained a biomedical version of Megatron. So one of the interesting things that has happened that we have learned in the last couple of years. So people often, when they're building these kind of pre-trained models, they will start with a general domain one. So let's say they'll start with BERT, trained on a whole bunch of Wikipedia text and books and all these things. And then they'll start to continue that pre-training with domain-specific text. So they'll get clinical text or PubMed articles, and they'll just continue that pre-training on. Now, the problem that you run into with this is that you're stuck with whatever subword vocabulary you learned from doing that initial general domain pre-training. You get much, much better results if you actually redo that pre-training from scratch. Most people don't do that because it's brutally expensive compute to do that training. We've taken that on because we have a lot of compute available to us. So we have trained a 345 million parameter version of Megatron, as well as some much larger ones that have not yet been released. But we showed that you get much, much, much better results if you can actually learn a biomedical specific subword vocabulary and train from that. So you can go and pull this model. There's a few different ones that we have. So we've only released the 345 million parameter ones. That's about the sizes of BERT large. But it's a good sweet spot because it's not too big to try to host and do some fine training on from yourself. Or fine tuning on for yourself. There's a few different versions of this with different vocabulary sizes, cased and uncased versions. Those are all on NGC. I recommend you go and play with them. This is where I spend a lot of my time is working with this. We use this for a lot of different healthcare applications. If you are doing work in chatbots, this is the task that's going to be near and dear to your heart. So typically, when you're doing a voice assistant, the NLP on that has two different tasks. There's intent classification. So what's the goal of the utterance? This person here wants to book a flight. That's what they want to do. And then there's slot filling. So this is a named entity recognition task, finding the little particular entities in it related to that intent that you need to carry out that task. So my source and my destination for this travel here. If you train those two classifiers together at the same time, jointly, you get much better results. So we've got some nice pre-trained BERT models that you can pull to do that. We have question answering that we've done as well. So SQUAD is kind of the standard benchmark for open domain reading comprehension. So the way this works is you give it a passage of text, say like a paragraph from Wikipedia, and you pose it a question, and then the task is to find the passage, so find the sequence of text in that paragraph that answers the question. We've gotten some pretty good results on models from this, and those are out there. You can get those as well. Not in NeMo yet, but coming very soon, is a new TTS model that we have called Talknet. Talknet does something interesting. So instead of having one model that's trying to generate the MEL spectrograms from the input text, we split that task. The first model says, given every grapheme, so every letter in that input, predict a duration from that. So this is that stretched out thing with all the tildes in the middle. So predict the durations for every grapheme. And then from that, then you generate the MEL spectrograms and then pass that into a vocoder. So that's two separate models. You can train those in parallel. You do need, in order to train the first one, you do need extracted durations, but we actually, we have a method of generating that just using one of our own speech recognition models. So please go try it out. It's all out there. It's all in the open. Documentation's there. Lots of examples, lots of tutorial notebooks. We've got dev blogs available as well. Tons of pre-trained models on NGC. So go take a look at NGC. You may be surprised of the fun stuff you can find on there. And then lots of best practices as well. Ali was very kind to ask this earlier, but yes, we absolutely adore our collaborators. We put this out in the open and develop it in the open because we want this to be a research tool that serves you. So if you're at a startup that's got some tools to help in a data ecosystem, or something else you think might be able to hook into this, please write some hooks to your own tools. Submit a merge request. We love it when people submit a merge request. It totally warms our hearts. But submit issues. Like we really pay attention to those. We also do research. We do joint papers with people outside of NVIDIA. And we're keen on that. If you have interesting things that you think are worth working on, there's opportunities to host applications on NGC as well, to host models potentially if this is something you're interested in, and data sets as well, sharing data sets, helping to build better pre-trained models that we can help distribute. So lots of different ways that we can push this forward together. That brings us to the end. Thank you very much, everyone. I'm going to bring back to the collaboration site page so we can look at that.
Awesome. That's actually my favorite slide.
That's why we're going to leave it here.
Yeah. Awesome. So we have a couple of more questions from the audience, also myself. Also, after that, we'll move to the facilitators. I'm pretty sure they have also questions. We have like about 15 minutes left, so at max. So one of our audience asked a questions related to the previous section. He or she asked, does the NeMo have any optimization and model quantization so that the model could be used on mobile or edge devices?
Oh, okay. So trying to take something of the size of BERT and then compress that down to an edge device, that does get tricky. You often end up having to do things like like distillation approaches to train that down. Now, that said, I recommend you take a look at Jarvis. So I talked about this a bit in the introduction. Jarvis is our framework for model deployment. Now, under the covers in Jarvis Jarvis is really running on the Triton Inference Server and TensorRT. TensorRT is what's doing a lot of that optimization. So the quantization, like a lot of that kind of stuff, to really compress that down and make that a lot more efficient. We have seen people do work of compressing models down and deploying them on things like Jetson devices. So like the edge, those edge devices. You could probably handle mobile as well, but don't hold me to that. If you have a particular use case, reach out to me and I can connect you with some people to see if we can work out that use case.
Awesome. I have a question myself. As a applied ML engineer myself, we tend to use transfer learning most of the time, and the first like challenging part is usually like create a proper data loader for your data, particularly for in a company you have a data set that is accumulated over time, and now they just these cool technologies came in and they want to do something about it, right?
Yeah.
So can you expand a little bit on the data loaders, like what formats are supported, like how people can do data transformation to make it compatible with NeMo?
Yeah, I mean, there's a bunch of so I spend most of my time in NLP, just because that's my background. So that's a lot of what I work on. Yeah, I mean, there's a lot of examples of data loaders that are in there. We've got scripts in there for like converting from like an IOB format of an NER data set into like what we particularly need in NeMo for training. Like there's lots of scripts for doing that kind of preparation. But then in terms of like the actual like Torch data loader, yeah, like our data set and data loader classes they're extensions of Lightning. So any of the notions of how you do like Lightning's use of data loaders is I think excellent. Like they've done a very, very good job making that really workable. So all those same notions about like iterable data loaders or batch data loaders, like all of that applies, and we have examples of using each of those cases, and we have some in there. So if you actually go and take a look in there about how the BERT pre-trainer data loader works, that's actually because obviously the full data set's not going to fit in memory. So that's an iterable set where you're actually going and iterating from an index in each of the batches. You go to find something you want in the batch, that's going to find it on disk. That's going to load that. There are some like pre-processed versions of this that will handle. So there's lots of examples in there about how to handle each of those cases. We also have a developer guide that shows you how to do more of these kind of cases as well. But again, like any concepts that you would want to carry over from Lightning about handling this will carry over.
Perfect, thanks. Facilitators, Gordon, Zach.
Yeah, sure. I was hoping to ask in terms of just generally about future directions with NeMo. Obviously, it's open source. I'm sure it'll go in many different directions. But curious what some of the focuses are at NVIDIA, and if you guys are considering some things like dialogue state tracking.
Oh yeah. So we actually have so we've got some dialogue state tracking in there as well, and there is more. Why am I blanking? I'm blanking right now about the actual name of the dialogue state tracker that we have. But yes, we've got new dialogue state tracking that's going to be coming at some point. We've got a lot of work happening right now on machine translation. That's a big focus for us. So you will see more of that coming in. And I would not be surprised if there ends up being more focus on some multimodal applications as well. So we've had a unification effort going on through some of these frameworks of tying together TLT and NeMo, but then also and then Jarvis, and then also tying together some of the other frameworks that we have, like DeepStream, which handles a lot of vision applications. So they're we don't have a lot of effort on that right now, but there has always been interest in pushing more multimodal kind of applications as well. Yeah. TTS I think is going to continue to be a big focus for us too. So I talked about Talknet coming out soon. That's also a strong focus for us.
And I also want to ask a follow-up on that. In terms of like building chatbots, do you have are you looking into stuff like policy optimization and reinforcement learning as well?
The team is aware of and interested in that. I can't really speak to whether that's something they'll be working on in the next little while. I think there's a lot of different things that we can be doing, and I think it would be great to see that. I'm not entirely sure whether we'd see that. So sorry for the only half informative answer, but I actually just don't really know about that one.
And on another topic, can you sort of walk us through, like, if I was a research scientist, then how would I be deploying NeMo models?
So what you get out of a NeMo model, so that you can turn a NeMo model into just an ONNX thing. So any way that you would normally deploy an ONNX model, you could deploy this. We have put a lot of effort into into getting this deploying very tightly with Jarvis. Jarvis will be in open beta very soon, just in the matter of a couple of weeks. So that's probably your easiest way to get something deployed as a researcher. We try to make that very very straightforward. But if you the thing with Jarvis though is Jarvis simplifies the tasks by focusing on particular applications. So like there's a gRPC interface for like NER. There's ones for like batch and for streaming ASR, and right. So very very particular tasks within that. It's not going to support all use cases. I highly recommend, if you don't fit in one of those use cases, just go take a look at Triton Inference Server, which then is also using TensorRT. Like those are really nice packages for deploying these models.
That sounds great.
I'm curious to get your thoughts on how you see deep learning, machine learning tooling evolving over the next couple of years, and sort of what role you see NeMo playing in that. Yeah.
I think in any case where you get like a big hype push on a new technology, you get a whole lot of these different kind of frameworks coming out, and then you get this shakeout once people go, I don't know how to make all these things work together. There's too many choices. I don't know what to deal with. We've kind of been seeing that shakeout, right? Like not a whole lot of people, sorry Google, but not a whole lot of people are really using TensorFlow that much anymore. Most of the effort on this, I think it really has gravitated to the PyTorch ecosystem. And the reason for that is because PyTorch has actually been very good at building an ecosystem of tools that are working together. So relatively recently, like PyTorch and the Lightning team have actually, like they've said, all right, let's make this happen. Let's make this work. Same with Hydra. We're very happy that we made that shift to focus on PyTorch, Lightning, and Hydra as our baseline. I think what you're going to see then over the next couple of years is just like more tools figuring out how to interoperate so that you can get an ecosystem that works well together. And I think the next step of this is going to be a lot of the data tools. So like Label Studio and Prodigy, like there's a lot of these tools that are excellent, and I think we're going to start seeing more work around just simplifying the flow around that. I've seen some really excellent startups that are really focused on like the workflow aspect of, say, like building and managing a chatbot. So I used to build chatbots at Nuance, back in like the early Siri days, when everybody was trying to do them and none of us really knew how to do it properly, and like the process of dealing with your data and designing that and managing quality on that is like just brutal. And I think there's some really excellent startups that are figuring out how to solve that problem well. And I think we're going to see more of that kind of effort too around these ecosystems of just like, how do I make this simpler?
Yeah, thanks for the answer. And I feel like tools like NeMo are also going to help make ML tooling more accessible to other engineers and people who maybe don't have or need as much machine learning background.
I completely agree. I mean, this is why we have high-level programming languages, so nobody has to write in C or assembly anymore, right? It's the same concept in machine learning.
Exactly. And I actually just want to add something to this. I completely agree. And right now, there are like so many good tools, but the problem is they are focused on one part and they don't work or interact well with each other. Whatever can make that kind of full stack workflow streamlined, like something like NeMo, that you can go from beginning to deployment, will become hopefully the mainstream and make it easy for us.
Yeah, and there's a huge opportunity for this too, because like most people who want a working system are not researchers. They're not that interested in trying to squeeze out an extra 0.3%. They're people who just want a working system. So and these are people who have enough commonality in their use case that you should be able to do this. We should be able to support that.
Exactly. Yeah, thank you so much. Is there any other question?
Not for me. Thanks, Chris.
Well, thank you, everyone. This is a great opportunity. This is always really fun doing stuff like this. I'm going to turn off my sharing, I think. There we go, so we can see faces again.
Perfect.
All right. Yeah, thanks so much for the opportunity. This is really enjoyable.
Yeah, if there is no other question, I would like to make a couple of points. If you want to rewatch this video and also access the PDF version of the slides, as well as a link to the NeMo's GitHub repo, as well as the NeMo's webpage on NVIDIA's website, you can go to the AI.SCIENCE, find the events page, and you can access all of those resources. If you guys have any final words, please go ahead.
Yeah, so I just want to say, like, thank you so much for coming out here and Christopher, talk with us and be able to explain a lot of pretty complex issues surrounding NeMo. I think it's a very great tool, and it's one of the tools that will greatly improve like the quality of the workflow around machine learning. And so thanks.
Thank you, Zach.
Yeah.
And thank you for joining me in my scenic basement.
Awesome. Yeah, then thank you so much, Christopher, Gordon, and Zach for joining us. If there is nothing else, one YouTube thing. If you like the video, smash the like button down there and subscribe to our channel. That's what I had to do it. Otherwise, we can close the call.